Good morning, everyone. It's time to begin. Welcome to the seventh seminar session of Mechanical Engineering 758 for the academic session of fall 2020. There will be two presentations today. And the first presentation will be made by Atriya Biswas, the title of which is Energy Management of Electrified Powertrains with Reinforcement Learning. Atriya, would you please address the group?
Yeah, thank you, Dr. Jed, for introducing me. Let me present my screen. Let me know, can you see my screen?
Yeah, we can see that.
Okay, thank you. Okay, I'd proceed. Good morning, all. I'm Atriya Biswas. I'm a PhD candidate under the supervision of Dr. Ali Mahdi. Today, I'm going to present some of the key aspects of application of reinforcement learning in energy management system for an electrified powertrain. If you remember, last fall I presented some key fascinating aspects of reinforcement learning, that it's one of the main foundation of modern AI, and it works almost in a similar way that human makes the decision making, and it improves the decision making process with past experience and past learnings. And the more it gets experience, the decision making becomes more and more improvised. But with that, for human, however you practice, however you learn, there is a scope of making mistakes after a certain training. But that's not the case with the machine, which after a certain point of training, it can always give the desired success. I guess with this introduction, I'd like to move to the introduction of an electrified powertrain. I'll give a very simple idea of electrified powertrain. Think about this situation when two cars, one with the conventional powertrain, one with the electrified powertrain, they are waiting at the light for the light to be turning green. As soon as the light turns green, there is a big torque demand for both the powertrains, because from the standing point, if you'd like to get going, there is a lot of torque demand. So think about the conventional vehicle. Since IC engine is the only propelling unit, at the low speed, if we see the engine speed and torque curve relationship, at the low speed it has low torque, which cannot suffice the output torque demand. That's why we need.
Excuse me, Atriya. Sorry, this is Sumant here. Is your presentation frozen completely? Because I still see only the first slide.
Okay.
No, it's not moving. I can hear you talk very clearly, but the slides are not moving forward.
Can we see right now?
Yes, now it's better. Now it's moving.
Okay. That's better.
Yeah. Sorry for that.
No problem at all. This is not your fault. Yes.
Okay. I can start again. If you remember that in the last fall that I presented, reinforcement learning is the key foundation of modern AI. It works in a similar way that human will make the decision. It learns from the previous experience, and the decision making becomes better and better as we get experience. And that similarly happened with the reinforcement learning agent too. But there is no guarantee. Okay, this is not moving. Okay, this GIF is not working. Okay, but there is no guarantee for human. However, we train ourselves, there is a scope of error after a certain point of training. But for the machine, after a certain point of training, it can always give the desired success. Now, with that introduction, I would like all to get familiar with the electrified powertrain. If we consider a situation when both these cars, they are standing on the light traffic and they are waiting for the light to turn green. As soon as that light turns green, there is a huge demand of torque for both the vehicle. And now this vehicle with the conventional powertrain, the IC engine is the only propelling unit, and at low speed, it can only generate low torque, but not the high torque. So that's why there is another component needed called the transmission, which will elevate the torque to suffice the torque demand from the vehicle. On the contrary, the electrified powertrain, which is mainly propelled by the electric machine, if we see the speed torque curve of the electric machine at the low speed, it can deliver a lot of torque, the maximum torque. So there is no requirement of any extra component called transmission. If we see for the conventional powertrain, at the low speed, low torque region, it's highly inefficient. It generates a lot of emission and a lot of fuel consumption. And compared to that, for the electric machine, the low speed, it has decent amount of efficiency. So from that, I would like to proceed to pros and cons of conventional vehicle in compared to the all-electric vehicle. The conventional vehicle has edges over the all-electric powertrain because their refuel time is minimum, there is reasonable initial cost, and we need not compromise anything on the performance. But there are some serious drawbacks such as the greenhouse gas emissions. More stringent laws from the regulatory body is getting stricter and stricter day by day. And as I have mentioned before, there is inefficient driving. In compared to that, all electric vehicle, there is no emissions. There's highly efficient driving, and more importantly, we can recuperate some of the energy that would have been lost during the braking for the full electric vehicle. But there are some drawbacks too. Range anxiety with a single charge and more charging time. Charging infrastructure has not been improvised that much in the mass scale and people perception. If we combine these, like the benefits of all electric powertrain and benefits of conventional powertrain, we can bring a hybrid electric vehicle. It can suffice all the requirement of traditional driving with more components. However, it will bring a lot of complexity in the system because now more components are there. There is engine, there are motor, there are battery, there are transmission, a lot of control units. Now the task of this, don't misjudge, this is not the driver, this is the supervisory controller. The task of that supervisory controller becomes so complicated because it has to control so many things. It has to assign the propelling responsibility during different times based on different driving situations. Now, for doing that, energy management system is one of the key supervisory controller aspect which needs to be improved in the electrified powertrain, specifically for hybrid electric vehicles. The primary objective of an EMS in an electrified powertrain would be to optimize the fuel consumption and greenhouse gas emission in compared to the conventional powertrain, given that the battery SOC, the charge of the battery should be sustained from the beginning to the end. Like the battery shouldn't be overcharged or battery shouldn't be over depleted. Now let's see what are the industry's perspective from EMS. what does the industry require EMS to perform? The EMS should be real-time implementable. The EMS should optimize the fuel consumption as well as the greenhouse gas emission. It should be computationally cheap. When I say it's computationally cheap, that means the computation effort should be as least as possible, and it should sustain the battery SOC. Global optimization control technique is one of the most accredited control strategy for EMS, which could be ideal. However, it's not real-time implementable. The global optimality of the control would be guaranteed, although it is computationally expensive. If we take, let's say we take a 30 minutes of drive cycle, and to obtain the global optimal control from one of the well-known numerical technique called dynamic programming, that can take up to 2 weeks to give of computational time to give the global optimal control. But it can guarantee the charge sustainability. So what are the other kind of most used EMS control technique? That's the rule-based control, which is real-time implementable, but the optimality is not guaranteed. It is computationally very cheap, although the task sustainability might not be guaranteed in a real-world driving scenarios. Now, looking at these things, what does the industry do? They first of all take some certain drive cycles, driving missions, and they apply the global optimization control techniques on those drive cycles, and they obtain the global optimal control, and then they do rigorous mathematical process to simplify those optimal control into some rules, and then they calibrate the supervisory controller. And believe me, like lots of workforce, millions of dollars are being spent to do this rigorous post-processing. Now, looking at the drawbacks of both global optimal control and the rule-based control, we need an updating control policy which can be real-time implementable. The rules for choosing the optimal control should be changing in real-world, real-time periodically, which was the drawback of the rule-based control, because that would happen the stationary. Once you deploy the supervisory control in the vehicle and you deploy the car on the vehicle, like road, you cannot change the rules. So we should have an intelligent algorithm, specific algorithm for changing those rules, and it should maintain the charge sustainability in the battery, and it should be computationally cheap also. Let's see what a reinforcement learning can do to suffice those objectives. We need to have an updating control policy at the end of the day, like or a certain training cycle. With that objective, reinforcement learning based EMS starts where it doesn't have any idea of what kind of driving mission it will going to experience in the real world scenario. It might not know even what is the destination. Then it will, as soon as the vehicle start, it will start gathering the data from so many sensors. I'm just mentioning few sensors like the speed, the battery SOC, accelerator pedal position. They are fed to the EMS, which is equipped with the reinforcement learning. And as soon as the vehicle starts, the reinforcement learning will decide an arbitrarily control action with the arbitrary rule, because at the very nation's stage, the rule is naive. Then the RL will observe the immediate consequence. The immediate consequence can be fuel consumption, the greenhouse emission for that single time step. And it predicts what would be the long-term emission, long-term consequence, or the long-term fuel consumption for the entire drive cycle. Based on that predictive long-term consequence, it will try to update the the control rule with some algorithm. These are the reinforcement algorithm. There are so many algorithms: TD learning, Q learning. Once the control law is updated, it's no more arbitrary, but there is a well balance between exploration and exploitation is maintained. Then the vehicle goes to the next time step, and the same loop uh, uh, starts happening. Like it keeps on going until the reinforcement learning makes the EMS enough competent for maintaining the charge sustainability as well as optimized performance. I have taken a few real-world driving scenarios, driving missions, and implemented the reinforcement learning as an EMS control strategy. And you can see after 600 driving cycle, like training cycle, we could have achieved like our first goal was to maintain the task sustainability. When it does that, then we took an arbitrary driving mission from an ensemble of lot of drive cycles, and we implemented the reinforcement learning, and then we compared with the global optimal control, what would have been given by the global optimal control, and we saw that the charge sustainability is quite decent. It started with 36 and it ended at 38, and then we saw that the RL based EMS can give only 11% more fuel consumption than the global optimal control. I guess with this, I'd like to thank everybody for paying attention.
Thank you, Atriya. A very interesting presentation. First question, Dr. Shankar, please.
Oh, thank you, Atriya. I was very fascinated by it. Even I remember your first presentation, which was on artificial intelligence introduction. So I was motivated to go read about it. I have a couple of questions. Just a philosophical question for once. The second slide you said the machines are prone to make less errors and humans are prone to make more errors. And I'm very intrigued by that logic with which artificial intelligence sort of takes on, right? So in my mind, the source of error is when you have an anomalous situation, basically. In a normal, like steady state situations, humans' errors, like driving in a highway, your errors are going to be much less. But if a cat crosses your path in a city, you're going to have more errors. So your fuel consumption, your energy management systems are more rigorous in a city driving situation where you have a lot of obstacles and hurdles and decision making points. In that cases, I feel that how does artificial intelligence system or reinforcement learning actually train the system to make split second decisions, which are randomly off from their standard decision making rules that can be reinforced? So how does that influence your energy management system? Because that, to me, fuel consumption is much higher in a city driving situation where you have a lot of hurdles and stop and go situation. But I would like you to address that from point of energy management and responses in terms of the robotic control versus human control.
Like for if you say the human like what would be in the real world driving scenario, how a human would behavior, and in compared to that, how reinforcement learning would behave in that situation. So that needs a lot of training. And like in the human, there is a scope of error always, but after a reinforcement learning that got trained after like and these trainings, they are rigorous training, and so far that's why the industry hasn't embraced this technology, because there is still some fault, like it's not still fault tolerant. That's why we researchers, we are investing our time, lot of time in making it fault tolerant, so that it can like we can always count on the reinforcement learning. Now on this slide, what I have shown that they are Boston Dynamics, and they are making their robots based on the reinforcement learning. robots are like quite fault tolerant. You kick them, you try to hit them with some bar. If they will again stand up, then they will accomplish the job they are assigned for. So that level of success, that level of like confidence has to be gained also in the energy management system, but it's still not being gained, that confidence. That's why we are working.
Thank you, Atriya. I'd like to move on to the next questioner, Dr. Yan.
Okay, thank you. Thank you for your presentation. So actually, I have two questions. The first one is, as we know, the reinforced learning is the computational cost is high. So how do you deal with this issue in real time? And the second one is the reinforced learning its performance is highly related to the data you use to train. So how do you guarantee the quality of the data for experiment and also in the application in the future?
Yeah, so for the reinforcement learning, the computation cost is still high. The with the present level of competency of the microchips, still high, because they cannot do like what MATLAB can do in a traditional computer. That cannot be done in a small microchip. So that thing is still under investigation. That thing is, we are not saying that at the present time it's computationally cheap. What we research, that we see whether it's capable of tackling the real world scenario or not, if sufficient data is provided. And now coming to the second point, uh, the quality of the data, quality of the driving condition. We have to make the vehicle equipped with the reinforcement learning. We have to drive the vehicle to different kind of driving scenarios, so that we can like make the reinforcement learning experienced enough to tackle all kind of driving situations. So that all depends on the quality of the data, and more and more it will get trained with the real world driving scenarios. It can address that quality issue. uh, I guess I addressed somehow. Like, I know the first one, the computational cost is still not cheap.
Thank you, Atriya.
Thank you.
There'll be one more question. Mr. David, please.
Yes, Atriya, it was a very interesting presentation. I just wanted to ask one question. I can see that your objective function is to minimize fuel consumption, and I can see the process is computationally expensive. So I was wondering what happens if the vehicle suddenly is unable to make a decision within a split second. Like, if an exception arrives, is there a mechanism by which the machine can just forget about fuel consumption and just handle the crisis, like to sacrifice everything else for computational efficiency and deal with the crisis at the moment? Is there a mechanism for that?
Yeah, so the energy management system is not just equipped with reinforcement learning. For some crisis situation, it will only uh, give some traditional, like, it will rely on some traditional control system, which will make the system fault proof. Suppose there is a sudden breaking condition. In that time, the reinforcement learning might not be equipped with the optimized control. In those cases, a fault tolerant control would be addressing that kind of situation. So when
With that,
when
I'd
we
like to bring this presentation to a conclusion in order to proceed with the next presentation. Thank you very much, Atriya. Very, very interesting presentation. The second presentation this morning is by Lucas Broek. Mark Drive A, Driving Simulation Lab in the McMaster Automotive Resource Center. Please, Lucas, address the group.
Hi, Dr. Jed. I still see Atriya's presentation. I don't know if I can
Yeah.
just like present over him. Or...
Atriya.